Alright, today we're doing lesson 6, bottom-up parsing. Let's go. So far we've been looking at top-down parsing. Top-down parser is limited in the grammars it can handle because it must be able to commit to predicted productions high in the parse tree based on relatively little information. For example, it must be able to choose the correct production from the start symbol based on the first token in input. This limitation motivates bottom-up parsing, in which the parser can choose productions after seeing more input. For example, bottom-up parsers can handle left recursive productions, whereas top-down parsers cannot. In fact, bottom-up parsers work best when productions are left recursive, although they can handle right recursive productions too. In the following figure, the shaded areas represent the part of the parse tree that must be predicted when some of the input has been read. Yeah, okay, so when a top-down parser reads the first token, they have to make an assumption that they have to basically make a decision to commit to a certain production, which can possibly eliminate a bunch of other options. Whereas bottom-up can, I guess, do it in a more granular way. Cool. Early parsing. A powerful yet ingeniously simple bottom-up parser is that due to J early, it can parse all context-free grammars, including ambiguous ones. Its worst case time is cubic in input length, but for most grammars encountered in practice, it takes linear time if implemented carefully. The idea of the early parser is to keep track of all possible parsers as the input is read. We can think of the parser as one that, unlike an LL parser, doesn't try to predict just one production. Instead, it blindly predicts all productions regardless of look ahead, spawning a new concurrent thread to handle each such prediction. Okay, spawning these threads would work in principle and would be able to parse any grammar, but would be extremely inefficient because an exponential number of threads would be created in general. Moreover, a huge amount of work would be repeated by different threads. So instead, an early parser simulates the work that those threads would do while ensuring that the work is only done once. Okay, the early parser proceeds one input position at a time, keeping track of all the information that would be needed to simulate the parsing threads. Okay, so we have a one input position, as in like the string we're reading, I'm guessing. We proceed by one token at a time. For each input position, J, an early parser builds up a set of items, I, J, representing the state of productions that might be used in the derivation. An early item has the form A tends to beta dot Y and a K. The first part of the item is the production A tends to beta Y from the grammar, with a dot located somewhere on the right side of the production to show how much of that production rule has been completed. Okay, so in this one, the beta will be completed, and we'll be doing the Y next. For production, with an empty right-hand side, like X tends to the empty string, the first part of the item has the dot. The second part of the item, K, is the position in the input where the parsing of the non-terminal A started, in terms of the number of tokens read up to that point. Okay, we can think of K as recording the position where the thread for this item was spawned. The algorithm starts by initializing the set I0, so I0 because we haven't read the first token yet, to S prime tends to S position 0, and the dot is here, so we haven't read S yet, where S is the start symbol of the grammar, and S prime is a new artificial symbol introduced to simplify the algorithm. Is a new artificial symbol. Okay. The algorithm successfully parses the sequence of n input tokens, A0, A1 through to A minus 1, if the item S prime is in the set I of IN. The algorithm successfully parses the sequence of n input tokens if the item is in the set IN. So this looks like it's completed. So if this is the first item where the dot is here before the S, this must be the final item indicating some finished state, I'm guessing, because the dot is after the S and position 0, meaning the first meaning I guess this means the entire thing has been done if this item is in the set, because we've gone through everything and we've completed it. The algorithm considers each input position j from 0 up to n. At each input position, it builds up the set ij by applying the following 3 rules as many times as possible until none of the rules has any effect. First one is a scan. If the set ij contains an item a tends to beta dot c delta k, so the dot is in front of C, where C is equal to the next input symbol, AJ. Then the item A tends to be C dot delta, so we move the dot over 1 and add it to the set. All scan steps can be done as the final actions at a given input position, since they don't affect ij. Wait. What's ij plus 1? Is added to ij plus 1. Is that 2 different sets? Wait. If the set ij contains an item, so the dot is in front of a C, where C is equal to the next input symbol. So if it's a terminal, I guess, then the item A beta C dot, yeah, so if it's a terminal, we move the dot over, is added to ij plus 1. What does it mean to ij plus 1, and we have ij as well? Does that mean it's a different set? I'm going to see if ChatGPT can figure that out. In the context of LR parsing, using the canonical collection of LR1 items, RJ refer to different sets of LR1 items. RJ represents the set of LR1 items at the jth state or configuration of the LR1 parsing automaton. Don't understand that. IJ plus 1 represents the set of LR1 items at the J plus 1th state or configuration, which is derived by applying certain transitions based on the LR1 items in IJ. The LR1 items are augmented production rules with a dot representing the position of the production in the production. For example, means that in state IJ, the parser has seen the production A, BC, delta, up to the point where C is the next input symbol and K is a look ahead symbol. That can't be right. I thought K was the index from where the production or from where the scan operation began. In the specific case, the quoted text describes the scanning operation if IJ contains LR1 item this, where C matches the next input symbol, A sub J, it's a fancy word for the next input symbol, then the LR1 item, then the item is added to IJ plus 1. This represents the transition to the next state after scanning the input symbol C. Okay, so IJ plus 1 is the set of LR1 items that results from scanning the input symbol at state IJ. The set of LR1 items that results from scanning the input symbol at state IJ. And it is different from IJ since it includes new LR1 items reflecting the progress of parsing after scanning the symbol. So it's okay, so it's just like the next state, I guess. It's the next state with the new item, like possible items, I suppose. Predict. If the set IJ contains an item, A tends to beta dot capital C delta. Okay, then for all productions, capital C tends to Y in the grammar. An item C tends to dot Y. J is added to IJ. Note that prediction steps can enable further prediction steps when Y starts with a non-terminal. So then for all productions, it looks like C itself is basically a non-terminal that contains more productions, because from all productions, C tends to Y in the grammar, an item C tends to dot Y, J is added to I, J. And J is the index we're looking at in the lookup, the input string, basically, or the index of the token that we're currently looking at. Note that prediction steps can enable further prediction steps when Y starts with a non-terminal. So if Y is a non-terminal, then we have to predict again. Okay. And complete. If the set IJ contains a completed item, C tends to Y dot, then for each item of the form, A tends to beta dot C delta L in set. Wait, is that I? I think that's an I. I in set I K an item a beta capital C dot delta. I can't tell if that's an L is added to I J. Probably gonna have to look at an example to understand this, but it's like completing something. So you're completing something. Obviously, you're completing the. You made it to the end of. You made it to the end of the. I'm not sure what this is, but the end of the production, I guess. These are the same three actions that we saw in the table. Yeah, in the table-driven LL parser, but unlike that parser, the early parser does not have to commit to its predictions. Instead, it handles multiple predictions and even completions in parallel. The predictions that do not pan out effectively die out because at some point they lead to items that are incompatible with the input tokens encountered. Okay. Consider the following grammar, which is not LL1. So, for it to be, I'm trying to remember, for it to be LL1, you have to, you can't have any productions with overlapping first values. And so this is definitely not LL1 because this, wait, let me think about this. Well, first of all, it's left recursive and left recursive because S appears before anything else. So left recursive is troublesome for recursive descent parsers or top-down parsers. And does this have overlapping first sets? I can't remember how to do this. Well, let's move on. It's left recursive, so therefore it's not LL1. It's got an LL parser is going to have trouble with it. Anyway, so S can be S plus E, or it can be E. E can be an N. I'm guessing that's a number by the looks of our input. And E can also be S within braces. So, for set 0, we start off with our initial production. The dot is on the left hand side of the S. Here's our input string. I'm going to highlight that. Then we need to, so we predict S because we're immediately in front of an S. So it looks like when we predict for all productions in the grammar, an item C tends to dot Y is added to IJ. So we add these two because S can become S plus E and it can become E. We haven't scanned these yet, or we haven't like processed them yet, so the dot is on the left hand side. So we now have to process these two. We still can't see. We still haven't seen like one of our inputs or anything yet. So to predict S, we can predict S again, but seems like you'd just be repeating yourself by doing that. So it looks like we start predicting E. So E can become N, and E can become S within braces, parentheses. Then looks like because we have yep. So one of these is a term. One of these matches the first symbol in the input. So E gives us braces, which matches this symbol in the input. Therefore, we scan that. So C is equal to the next symbol AJ, then the item for the beta C dot delta is added to I J plus 1. Okay, that's why they added it to the next set. That makes sense. So from this step here, step 5, we look at our input token, which we are here currently. We see that that this matches. So we scan it, and with the scan, what we do is we put it into the next set. And then from then on, we have to process the next input, the next non-terminal, which is S. So we predict S, and S can become S plus E, and it can become E. So look ahead token is now, we're at position 1 in the input, which corresponds to here. Not our look ahead token, our input token is now a 1. So to get a 1, we have to predict E, which gives us this N. Since we can predict E, we can do a scan on here. At step 9, we can scan N. That puts us into so that puts us into the next set here, where we scan it in. We still haven't scanned S tends to E, so I'm guessing that's the next one. Wait, what are they doing? So they're completing E. Right, because since we finished an E here, we can complete E. What does complete do? If the set IJ contains a completed item, then for each item of the form A tends to beta dot C delta in set IK, an item A beta C dot delta is added to IJ. So we're adding it to the current set that we're in, since we've completed E. Why are we... I'm not sure. What are we doing here? It's complete E. I'm not 100% sure on this step. I get that we're completing E, but then we have to go back a step. So we have to move the position back one. So we're completing, okay, so we're completing E from step 11, makes sense, and step 8. Oh, okay, so we predicted it here. We complete it. So we've finished this one, we've finished step 8. Then we complete S. Why are we completing S? Oh, okay, so we completed S because this S is the result of this predict, where we predicted S from here. Oh, okay. There's a lot to keep track of. I guess that's why they're writing the from. Makes sense why they're writing from steps. Okay, there's a lot to keep track of. We complete E from step 11 and 8. Complete that E, which then completes this S up here, which leaves us with this to finish. So we can do a scan on the next step by the looks of it. We also complete S from step 12 and 7. So we've moved the dot. So when we predicted, we move the dot from here to here, and then looks good. So now what we can do is we would have to do two things. We would have to scan this, and would have to scan this. So this is actually the next input symbol. But it doesn't look like we're able to move. It doesn't look like we're able to move our position up because we're still at position 0. We complete S. No, so we do scan it. So we scan from 13. We scan the closing parentheses, which allows us to complete E. And that E came from step 3, way back here. Okay. Then we can complete the S from step 1. And then we can complete S from step 2. Then we would scan the plus, and so on and so forth, until eventually we achieve this state where we have S prime tends to S and it's completed. But we do achieve that up here. I'm not sure why that doesn't work. Let's have a look. 17. We can visualize the action of the parser by drawing a graph, showing how the various steps depend on each other. Step 17 just doesn't go anywhere. Step 17 never leads to the scanning of the next, this plus symbol. So in 17, it looks like we've finished, but we're unable to scan the next input token, therefore we don't do anything, it just gets stuck. Step 18, we complete S from all the way from the second step, which was, yep, that was that S, and then we're allowed to scan the plus symbol, and then we have to predict E. Then we scan a number 2, we complete the E, and that allows us to complete S, ending at step 24 when we get there. Okay. Here, the scan actions are annotated with the token scan in blue. The dashed arrows show the state advanced by completions. Yep, and are labeled with the non-terminal being completed. As this graph shows, the parser explores some states that do not lead to the successful parse, but these states, 4, 10, 17, 14, 21, quickly get stuck because they're unable to scan matching input. Removing these states and looking just, so state 4, it tries to scan a number, but there is no number at the start, so therefore it just gets stuck. State 10 and 14, state 10 tries to scan a parentheses, but there is no parentheses at position 1. There's only a number, therefore we get stuck. State 14, we try to, looks like it tries to scan a plus, but there is no plus in the input. The next symbol is this. Sorry, there's no plus at the current input token. Yeah. 17 and 21. What does 21 do? 21 tries to scan parentheses, but there is no parentheses at position 4. 1, 2, 3, 4. There's only the plus. So it gets stuck. Okay. So removing these states and looking just at the sequence of completed productions leading to the success at step 24, we'll see that they describe a derivation of the string. S prime produces S plus E. That tends to S plus 2. That tends to E plus 2. That tends to S in brackets plus 2. That tends to E in brackets plus 2. Tends to 1 plus 2. Note that at each step, the rightmost non-terminal is expanded using some production. The rightmost non-terminal is expanded using some production. Well, if you read it backwards, yeah. Cool. If you read it this way, yeah. However, the parser completes these productions backward. So it generates the rightmost derivation backward. Let's have a look at that. Generates the rightmost derivation backward. Okay. Starting from the input and ending with the start symbol. This backward construction of a rightmost derivation is what bottom-up parsers do. I probably need to see this like more in action to be able to understand that. Early parsers run in worst case time cubic when carefully implemented. On unambiguous grammars, they take worst case time of quadratic. Intuitively, the reason early parsers are polynomial rather than exponential is in the worst case, is that they share work among the different threads. For example, notice that the single completion of production S tends to E dot at step 12 does work for 2 threads that work off at step 6 to states 7 and 8. So step 12. Step 12, when we complete the E from 11 and 8, obviously we finish this one, and then we finish step 8. That also completes 6 and 7. Wait, does it? Oh no, it doesn't complete 7, but it does work for these two. That makes sense. Notice the single completion. The 7 thread gets stuck eventually because it does not see the expected plus on the input, but the other thread continues to the end. On LL or LR grammars, early parsers are even more practical, taking linear time when carefully implemented. Our example grammar turns out to be an unambiguous LR grammar, which is why the graph of states above is mostly linear and little work is wasted. Example grammar turns out an unambiguous LR grammar, which is why the graph of states above is mostly linear. Cool. Yeah, so you see there's not that many wasted states. There's a few, but it gets there in the end. Pretty cool. One simple and useful optimization is to complete productions only when the look-ahead token is in the follow set of the non-terminal in question. It can also be helpful to memorize cascaded prediction steps. I was thinking that actually. I was thinking, yeah, memoizing the results of these. I don't know, you tend to see this, seeing this a lot. Yeah. S tends to E. Where am I? A further improvement that avoids redundant computation is suggested by Aycock and Horsepool. In the predict step, when the symbol C is nullable, the item A tends to beta C dot Y is immediately added to the state IJ. They report that with this and other optimizations. Okay, so if C is right, so if C is nullable, you just immediately complete it. Basically, you essentially immediately complete it. They report that with this and other optimizations, early parsing is only 50% slower than Bison LALR parser, a reasonable trade-off given the improvement in parsing power. Cool. LR parsing. LR parsing, including LALR parsing, is a popular way to parse. It is the underlying technology in a number of parser generators such as Yak, Bison, and Cup. We can view LR parsing as an optimization of early parsing in which all predictions are pre-computed. LR parsing consists of 2 actions, shift and reduce. So LR parsers are called shift-reduce parsers. Make sense? The shift action corresponds to the early scan action, okay, followed by as much prediction as possible. The reduce action corresponds to the complete action, again followed by prediction. Okay. Rather than keep track of all possible rightmost parsers, a shift-reduce parser only keeps track of a set of parsers that correspond to a single rightmost parse. This limitation allows the state of the parser to be simpler than in the early parser. The state of the parser is based on a stack of symbols. like in an early parser, the parser builds a rightmost derivation backwards. With productions completed to the left of the current input position. Okay, that last bit makes sense. Still don't understand building a rightmost derivation backwards. Hopefully we'll be able to see it better this time. The stack of symbols is exactly the part of the current derivation state to the left of the input position. The stack of symbols is exactly the part of the current derivation state to the left of the input position. So here's the stack. It's exactly the part of the current derivation state to the left of the input position. So you slowly build the derivation. You slowly build it up. Okay. Therefore, at any point during a shift-reduce parse, the current state of the derivation is the concatenation of the stack with the unscanned input. Okay, so right, okay, yeah, well, yeah, it's visually laid out here. So the derivation e plus 2, you just concatenate the stack with the unscanned input. The derivation here is the stack concatenated with the unscanned input. So, okay, so you derive it as so you're deriving the entire thing as you're moving through the input. For example, we can write the parse of the example expression 1 plus 2 as a series of shift and reduce operations that build exactly the same rightmost derivation as the early parser did above. Alright, so we do no action, we have our derivation, our current derivation, and our unscanned input, we have nothing on the stack. Then we do a shift, derivation is the same, this is on the stack, unscanned input is the derivation is the concatenation of the stack and the unscanned input. So shift must, yes, it's like a scan. It was saying up here shift. Shift is the same as scan. So we basically put it onto the stack with a shift. Shift again. Yep, puts the next item onto the stack. Reduce, E tends to N, because so N means number, so we can reduce 1 to E, or we can reduce E to S, so E becomes S, we still haven't, so current derivation is S plus 2, then we have to shift the next symbol onto the stack, so we shift it from here to here. Then because of our grammar, what was that grammar? Yeah, S can be equal, sorry, E can be equal to S within braces. Looks like, yeah, so we shift the braces, becomes E. Sorry, we reduce it, my bad, we reduce it. Then we reduce E to S. We still have this left to scan. We shift the next symbol, S plus, can't do anything there. We shift the next symbol, S plus 2. 2 can be reduced to E, thanks to this rule. So now we have S plus E, and we know S plus E can be reduced because it's in the grammar. So if we finally finish with S. All right, cool. It seems a lot easier. That's actually a lot easier, ridiculously easier. What was this? LR parsing, and that was early parsing. So LR parsing is like way simpler. To determine what action should be taken each step, the parser needs to know what are the possible future productions to produce. The possible future productions are a set of items closed under prediction. This set of items tells us which actions make sense at a given point in the parse. To map a stack into a set of items, these item sets can be interpreted as a deterministic finite automaton that reads the stack and whose states are exactly the sets of items. Okay. These states look similar to early sets, but have the property that, ignoring prediction, only one meaningful action can be taken in each state, either to shift or to reduce a particular item. The initial state of the LR0 automaton corresponds to the early set I0, except that we add the end of input symbol to the top level production. Just like the early set, it is closed under prediction. So our original grammar was this. So original grammar was this. Then we add on S prime points to our original grammar with the end of input symbol at the end. The automaton is constructed by repeating the following procedure until no further change is possible. Choose a state and a symbol that lies to the right of the dot in one or more productions. Shift that symbol to the right in those items and close the item set under prediction. Not sure what that means, but I'm sure we'll find out. The resulting item set may be either an existing automaton state or a new one. In either case, add a transition on the chosen symbol from the old state to the state for this item set. For example, taking a transition on the token, open parentheses, from the initial state shifts just the final item right to obtain a state containing the production. E tends to S within parentheses, the dot's there, on which we then take a production closure that adds items for S and then E. Taking a transition from the same state on the non-terminal S, taking a transition from the same state on the non-terminal S, shifting the first two items right to obtain the items S prime tends to S. Completed. Oh, actually not completed because we have to complete the end of symbol, end of input symbol, and S dot plus E. Prediction closure does not add any items to this state. The following figure shows the steps you might take in completing the automaton. In the figure, the states are numbered in green, and the states in which a reduce action is to be performed have a thicker border. Alright, so we start with the top level. We take the closure on else, as in, I'm guessing we were just like doing a predict, or it's like a, yeah, basically a prediction. Then, what do we do next? We take the closure on E. Then what are we doing? We can scan E. That'll give us our first input symbol. Why did it do that? Transition from state 0 on N to form new state 1. Why did we do that? I'm very confused. Alright, let's see where it goes. I'm still trying to decipher this. Transition from state 0 on n to form a new state 1. All right. Transition to state 0 on. Oh, okay. We're just building an automaton. We're not actually doing a parse. We're just demonstrating it as an automaton. Transition from state 0 on open parentheses. That makes sense. So it looks like you just add everything beneath it. Oh no, okay. So I see. You transition from state 0. It's the same thing as scanning the open parentheses. So you scan the open parentheses, then you have to predict S. So you do your prediction. Then you can do the same again. You can, let's say you did a scan on N in this case, then you would point it up here. So you would point to state 1 from state 2. Let's say you did a scan on another open parentheses. I guess you would point back to yourself. If you did a scan on E, sorry, you would have to do a predict on E. So I think predicting E would be a new state. I think. No, E's already predicted. It's already done here. So I think you can go to 2 different states here. You can go to state 1 and you can go back to yourself. Transition from state 2 on open parentheses and N to existing states. Yep, cool. Then what else can you do? What else are we missing? We're missing the S up here, I think. We're missing a transition. No. Well, no. The next step would be. The next step would be the plus symbol, I think. Transition on the plus symbol, right? Transition from states 0 and 2 on E. Okay, makes sense. When you complete E, right? Yeah. Okay, because after we complete these, after we complete this one specifically, we will complete E. So therefore, we need a new state to go to, and then on S. So we'd now be in this state. If we scanned S from here, if we predict S from here, where do we go? We don't go back here. I guess it would be a new state. Yeah, so on S, we'll go to E, S, dot, okay. And then from here, we can do the plus. And so we can, from here, we can scan plus and we can scan open parentheses. Sorry, close parentheses. Scan plus, scan close parentheses. We complete E over here. Scanning the plus would lead us to having to predict E again, and then from E we scan a number, would go to here, and then if we scan the open parentheses, we'd go all the way back here. What if we scanned? So this is complete. So that's a reduction. So what do you do when you reduce? That's fine. So if we scan an E here, oh, okay, right. So scanning E there. I'm sorry, predicting E there would mean you have to reduce. If you see an S from here, okay. All right, my brain's a little fried right now, but I get the gist of it. I see how it's building this automaton. Still a little iffy on the reductions, but I get it. Like you're doing your shifts and then reduce, shifts, reduce. That looks like one of the final states, I guess. End of input symbol. Okay. All right. Definitely gonna need to go over that again, but I get the gist of it. We can summarize this automaton with two tables that can be used to drive a parser. The first is the action table, which tells a parser what to do in each state. Given the look ahead symbol, either shift and go to a new state, or else reduce some production. Okay, so that's what, yeah, so that's what we'll do. Shifting, well, I call it scanning and completing, but same thing, shift and reducing. Given the look ahead symbol, either shift and go to a new state, or else reduce some production. The second table is the go-to table, which tells the parser what state to go to when it reduces a production. Yeah, how do you actually determine that? So let's continue. So when you reduce a production, how do you know where to go at that point? So when we reduce from here, is that just it? Because it's that reaches a terminal, that completes a terminal, and that's not completing a terminal. I will definitely look at this again. Second table is a go-to table. It tells the parser what state to go to when it reduces the production. Below are these two tables for the automaton we just constructed. Side by side, empty entries in the tables correspond to syntax errors. Numeric entries in the action table correspond to shift actions. A production in the action table indicates a reduce action. A production indicates a reduce. Okay. So from state 0, if we encounter an N, we go to state 1. And we... Wait. What is 8? Oh, if we encounter... I see. So we have all our terminals here and our non-terminals here. If we encounter the non-terminal S, we go to state 8. Yeah, okay. Pretty simple. So if we're at state 1 and we encounter any terminal, we reduce E to N. That doesn't seem right because you can't reduce, that's not a number, so you can't really reduce that, right? Maybe I'm misunderstanding. If you're at state 3, you're reducing E. if you're at state 6, etc., etc. A shift-reduced parser operates on such a table. It has a stack of states rather just a current state, as in a finite automaton. It starts with the stack containing the initial state and no input is scanned. As it reads each input token, it looks up in the action table what is the current action for the state at the top of the stack given the next token. If the action is a shift, it pushes the specified state onto the stack. If the action is a reduce, it pops the number of items in the production off the stack and uses the go-to table from the state now at the top of the stack. Using the go-to table from the state now at the top of the stack to determine the next state to push onto the stack. Let's try this parser on an earlier example. This input sequence of tokens. The initial stack is just 0. To hopefully make it clearer, states on the stack are shown in blue and are predicted by the symbol that was followed to get to this state. These symbols correspond to the part of the derivation that has been constructed so far by the parser. Stack contains nothing. Shift action shift 2. Shift 2. Yep, so you shift the input on, you reduce. When you see a reducible symbol, we will actually reduce twice here. Shift the next one on, reduce that, reduce again, shift, shift, reduce S plus E, S, S, yeah. Notice that the LR construction we've seen so far does not do anything but reduce to a single fixed production, regardless of the next token input. As a result, the states containing reductions, states 1, 3, 6, 7, 9 in the example, states 1, 3, 6, 7, and 9, all ignore the look-ahead token. Hence, we call this an LR0 parser. By filling in the action and go-to tables in a less constrained way, we could obtain a more powerful LR1 parser. However, we will need to extend the LR0 construction that we just saw in order to obtain this increased expressive power. A simple but surprisingly effective extension to LR0 is to only add a reduce action to the action table in the case where the look-ahead token is in the follow set of the non-terminal being reduced, since otherwise the production is clearly not leading to a valid pass. That makes sense? When this refinement to the LR0 construction produces a valid shift reduce parser, we say that the grammar is SLR, simple LR. By adding reduce actions to the action table conditionally on the look ahead, the SLR exposes more of the power of the shift reduce parser. However, even simple LR construction does not exploit the full power of a shift reduce parser. For this, we need the LR1 construction. Cool. Cool. I definitely am going to go over these and redo them. This sort of stuff is probably in the homework, so I'm definitely going to be referencing this page again. And also, for the LL parsing one last lesson, I looked up some videos on YouTube, and for me, it's so much easier just seeing someone work through it, and then you just realize, you know, the basic instructions and things, like each little step to do, and it all becomes clear when you see someone else do it. So if you're struggling with this, definitely do that. I will definitely do that after this video. Anyway, next lesson we'll get on to LR parsing and parser generators, and then looks like homework 2 comes out, and then a couple more lessons, and we'll be ready to attack programming assignment number 2. So this one's going to be a tough one, I can already tell. Alright, thanks for watching. Cheers, bye.